Hi students, now we are going to derive an expression for the moment of inertia of a uniform disk. Disk means plate, circular plate. Axis passing through its center and perpendicular to its plane. Same like ring. Ring is hollow, but disk is a complete circle. Okay, it is not hollow. It is a plain circular disk. So we can take this is a plain circular disk. The circular disk is assumed to be made up of so many coaxial rings which are kept one above the other. See, for example, I will take one small circular piece. Then surrounding that I will keep one ring. Okay, this ring. Then again next another ring. So next another ring, coaxial ring, if I keep means totally it appears like what, a circular plate. So we have to imagine. Okay. Now this is the axis of rotation passing through the center. Here capital M is the mass of the circular disk. So capital M is the mass of the total circular disk. And capital R is its radius. Okay. Now, since it is circular, what is the area of this circular disk? It must be equal to pi r square. So pi r square is the area of the circular disk, where r is the radius of the circular disk. Now, since this disk is assumed to be made up of coaxial rings, keeping continuously increasing radius, rings of increasing radius are stacked one over the other, okay, so that it appears like this. So one ring at the center will be coinciding with the axis of rotation, and the last ring will be at a distance equal to capital R from the axis. Now in between the center and the circumference I will assume one elementary ring. Okay, you can see that shading also. So this is one elementary ring in between the axis and the edge of the plate. Okay. So this elementary ring is at a distance of x, small x, from the axis, and its thickness is how much? Dx. So what is the radius of the elementary ring which we have assumed is small x? What is its thickness? It is dx. So, how to find the area of that considered elementary ring? It is equal to the circumference into thickness. Is it not? So, I have assumed the elementary ring of thickness dx and radius x. Now, you can see here its mass is dm. Okay, the elementary ring is having a mass dm. So, dm represents the mass of a small element. Then dx is the thickness of the small element. And 2 pi x, 2 pi into x is the circumference of the small element. It is a ring, elementary ring only. Understand that? Now, the area of the ring is given by 2 pi x into dx. So, 2 pi x is a circumference. If it is multiplied by the thickness, what you will get is the area of that elementary ring. Understand? This is the only point you have to understand. So, 2 pi x is the circumference of the elementary ring, its thickness is dx. If you multiply these two, what you will get is the area of the elementary ring or disk. Okay, no problem if we call it as disk also. Okay, now here I introduce a new term, that is mass by area. The mass of the circular disk divided by its area pi r square must be equal to the mass of the elementary ring divided by its area 2 pi x into dx. Okay, so 2 pi x into dx, and this ratio will be a constant because we have mentioned it is a uniform disk. So what do you mean by uniform disk? Everywhere it's a density, that is surface mass density. This is called the surface mass density. It must be constant. So this is called by the name surface mass density. If it is one dimensional object, means in the previous derivation we used linear mass density, mass by length. Is it not? And now it is surface area, therefore it is called a surface mass density. And this must be a constant which is denoted with a symbol sigma. Understand? Any portion of this disk, if you take a portion and measure the ratio mass by area, it must be a constant. Okay. So from this equation, total mass of the disk divided by the total area of the disk must be equal to the mass of the elementary disk or ring divided by its area 2 pi x into dx. So from this I get an expression for dm. That is the first step. dm. Okay. So from this I can write dm. Okay. dm is equal to m by pi r square. So m divided by pi r square into 2 pi x into dx. So this is 2 pi x into dx. So you should not confuse this multiplication symbol with the x. So I keep one dot, m by pi r square into 2 pi x into dx. So this is our equation number 1. Have you understood up to this? So the mass of the elementary disk or elementary ring of radius x is m by pi r square into 2 pi x into its thickness dx. Okay, what next we have done in the previous derivations? First we have to find the opposition offered by this elementary disk, understand, to the rotation of the disk, that is moment of inertia of this elementary disk, okay, elementary disk or ring, no problem. So this elementary disk that is given by di, that is equal to mass dm into distance square. Okay, this is the equation 2. So what is the distance of this elementary disk from the center of this axis? It is x, is it not? So its mass is dm and distance square, because moment of inertia mathematically, dimensionally, it must be equal to mass into distance square. So the elementary mass is having a dm and its distance is x, so we have multiplied, and therefore the moment of inertia of the entire circular disk, okay, entire disk is capital I is equal to integral of di, that is equal to integral of dm into x square. This is equation 3. Okay. Now in place of dm, what we have to substitute? Dm is equal to what? M by pi r square into 2 pi x into dx. I am going to substitute for dm. And what are the limits of the integral? That is very interesting to note. Is it not? The limit here, x is the variable, because I told you the ring which is in contact with the axis, for that x is equal to 0, and the outermost ring is at a distance equal to capital R from the center. Very easy to understand, is it not? First ring means which is in contact with the axis, central ring. Okay, that elementary ring is at a distance x is equal to 0 and x increases. And finally, the last ring which is coinciding with the circumference of the disk, that must be at a distance equal to R. Therefore, these limits are 0 to capital R. Now, just substitution for dm and integrating for the variable x. So, I is now equal to integral 0 to R limits. Instead of dm, what shall I write now? M divided by pi r square. So, m divided by pi r square into 2 pi x into dx. So 2 pi x into dx. Only for dm I have substituted. What else is there? X square is there? No. So into x square. Okay. Now this pi term alone will be cancelled. Okay. So what are the remaining terms? 2m by r square. So this is now equal to 2m divided by r square into integral 0 to r, x into x square is x cube dx, x cube dx. Now the integration to be used here is what? Integral x power n dx. is equal to x power n plus 1 divided by n plus 1. Is it not? See, I will write the integral also. So, integral of x power n into dx is equal to x power n plus 1 divided by n plus 1. So, this is the integration to be applied here. So, what is the value of n here is 3. So, n plus 1 is 3 plus 1, 4. Denominator is also 3 plus 1, 4. Therefore, moment of inertia I is equal to 2m by r square. So, this is 2m divided by r square into, this is x power 4 by 4. So, this is value of the integral is x power 4 by 4 between the limits 0 to r. So, this is equal to 2m divided by 4r square. This 4 is a constant. I am taking that out into, so x takes the upper limit first minus lower limit. So, upper limit is r. So, it becomes r power 4 minus 0. Lower limit is 0. It vanishes. So, here this 2 by, this is equal to 2m into r power 4 divided by 4 r square. So that this 2 2's are 4 and r square get cancelled with this r power 4 and remaining power is 2. So this is equal to m r square by 2. Therefore the moment of inertia is equal to half m r square. Now, just before this, we derived an expression for the circular ring having the same mass and same radius. For that only, the moment of inertia we got as mr square. For the circular disc, it is half mr square. Understand? Same mass and same radius. So, what is to be understood here in all such derivations? If the object is one dimension, means find the ratio mass per unit length. That is a constant. That is called as linear mass density. If the object is two-dimensional like circular plate or a rectangular plate like that, then you have to take surface mass density. That is mass by area is a constant. So we assumed this entire disk to be made up of continuously increasing radii. That is the rings of continuously increasing radii. And we integrated between 0 to capital R. So, as usual, the moment of inertia of a single element we have to find out. Then, for the entire disk, we have to integrate for the value of x starting from 0 to R. And finally, we got that moment of inertia is equal to half mr square. I hope you must have understood well. Fine.